Welcome back to The Explainer. Today we're stepping right into a grand, almost Victorian-style library in London. Just picture it, an environment where code craftsmanship is literally everything. We're going to eavesdrop on Margaret, who's this brilliantly seasoned senior software engineer, and her rather eager junior colleague, Timothy. Just by listening to their back and forth, we're going to uncover some incredibly secretive, under-the-hood mechanics of Python memory management. And trust me, understanding what CPython is actually doing down there, it's a total game changer for how you review your code. Okay, so let's set the scene. Timothy just finished his first script of the day. He set up two distinct string objects with the exact same text, and he's sitting there proudly assuming they're hanging out in two completely different locations on the heap. I mean, two separate assignments, right? Makes perfect sense. But then, Margaret leans over and hits him with this absolute gem of a question. Are you assuming Python treats memory the way a human treats a printing press? It's such a brilliant way to phrase it, right? Because Timothy genuinely thought every new variable assignment meant clunking down a brand new physical copy in memory. Yeah, so Timothy thought his two separate assignments strictly guaranteed two totally distinct memory allocations, which, hey, is completely logical if you're thinking like a normal human being. But Margaret has to break the news to him and, well, to us, that the CPython interpreter does not think like a human. She puts it so simply. Python is lazy, and memory is expensive. When dealing with certain immutable objects, Python just straight up refuses to do the heavy lifting of carving out new heap space unless it absolutely positively has to. Now, to actually prove this, Margaret tells Timothy to fire up his interactive shell and introduces him to the IDW function. She wants to look at the literal fingerprints of his strings. If you haven't used it, the IDW function is basically the ultimate truth teller in standard CPython. It gives you the actual raw memory address of an object. Margaret points out that, look, values can easily lie to you. They make you think you're holding two completely separate objects. But IDW, it absolutely cannot lie. It completely strips away the illusion of variable names and shows you the raw hardware reality. So instead of wasting time carving out two separate memory blocks for Timothy's identical strings, CPython pulls off a really clever trick. First, the interpreter spots the string literal and realizes, hey, this is immutable. Second, it creates the object exactly once, just once. And then for step 3, it simply points multiple variables to that exact same memory address. CPython actually interns the string. It's kind of like taking two different sticky notes with different variable names on them and slapping them onto the exact same physical object. Timothy typed the string out twice, sure, but Python only built it once. But here is where Timothy's brain practically short-circuits. Margaret tells him, okay, let's switch gears from strings to integers, and they set up a side-by-side test right there in the terminal. First, they check if the memory identity of 256 is the same as another 256. The result? True. Makes sense, right? But then they check the very next number. Is 257 the same identity as 257? And the terminal spits back, false. Wait, what? The exact same logic that worked flawlessly for strings and perfectly for 256 suddenly breaks the second they go just one digit higher. So Timothy is just staring at his screen, and he's asking the exact same question we all would. Why on earth does 256 return true, but 257 returns false? Honestly, it feels like a glitch in the matrix. I mean, to Timothy and to us, they're just numbers. Why would 257 suddenly break the rule that 256 just followed without a hitch? This is where Margaret gives that classic, knowing senior engineer smile. She explains that to the Python interpreter, these are absolutely not just numbers on a screen. That specific number, 256, represents a hard-coded critical safety boundary within Python's memory management system. It's literally a line drawn in the sand by the very people who designed the language. To really get why this happens, we actually have to rewind the timeline to before your program even starts running. Right at t-1 millisecond, the moment CPython starts its boot sequence, it kicks off this fascinating optimization. At t0, it goes ahead and pre-allocates a massive global array specifically for small integers. And the range? Exactly -5 up to 256. So by t+1 millisecond, when you write code asking for the number 256, you are not creating a new object at all. Python just hands you a pre-existing recycled object straight out of that cache. And that right there is why 257 is the culprit. Because 257 sits just outside that pre-allocated safety boundary, Python is suddenly forced to act exactly like that printing press Margaret was warning about.
For 257, and literally any number higher than that, the whole lazy optimization trick just completely shuts down. The interpreter is forced to carve out entirely new, distinct blocks of memory on the heap every single time you assign it.
Which brings us right into Margaret's cheat sheet, identity versus equality. Okay, so this cheat sheet is something you really want to lock into your brain. Here's the deal. The double equals operator is your tool for checking equality. It's asking, do these two objects contain the exact same data? And honestly, that's what you're going to want to use 99% of the time. The is keyword, on the other hand, strictly checks for identity. It's asking a much more rigid question. Are these two variables pointing to the exact same ID address in memory? Two completely, fundamentally different questions. And here's why getting this wrong is such a huge deal. If you blindly throw around the is operator instead of double equals to compare values, you are basically setting a trap for yourself. You are introducing silent, potentially catastrophic bugs straight into production. Think about it. You run your local tests using small, dummy data, maybe IDs under 256, and everything passes with flying colors because the cache makes those memory IDs match. But then you push to production. A real user logs in with an ID of, say, 257, and boom, the code fails spectacularly because those memory identities instantly diverge. So Margaret's big takeaway for Timothy is super clear. In Python, variables don't actually hold values. They're just references. They are name tags pointing to objects. And honestly, until you check that IDNR, you really don't know who you're dealing with under the hood. So here's my question for you to take away from all this. Go take a look at your own codebase today. Are there silent memory threshold bugs just hiding out in your recent pull requests? Have you been secretly falling into that is versus equality trap without even realizing it? Keep Margaret's library ledger in mind the next time you write a comparison and see what you find. Thanks for joining me for this explainer, and I'll catch you in the next one.